if I'm not wrong, last Tuesday we started describing this architecture, which is a protocol layer architecture for ISDN, in particular for the ISDN-B channel, which is the channel devoted to the exchange of data traffic, which means packet exchange. It's basically organized in 3 layers. One is the physical one. Actually, typically, physical layer supports several standards depending also on the transmission medium, etc., but it's not so important from our perspective. Then we have a protocol of layer 2, which is called LAP-B, LAP-B, and then the so-called X25 packet layer. And basically, we summarize the main functionalities of these 2 layers, stating that there is an error control in layer 2, in LAP-B, and since this protocol architecture is repeated every link, it implies that we have an error control link by link in the overall network architecture. Furthermore, we have an X25 packet layer on top of that, which allows us to open several logical virtual circuits at a user premise, typically to be connected with possibly the same set of destination user or different users depending on the user need. So that's basically the main features of this architecture. So this is a summary of what are the main features in the 3 layers. Let's forget about the physical layer, which is dealing with anything related to physical layer issues, transmission, power, voltage levels, and timing, and all these kind of things, connectors, type of media. In the data link layer, which is derived from a very old protocol, which is called HDLC, which has been defined in a very peculiar scenario, which was not even a networking scenario. There are 3 main features we wish to highlight. One we already discussed is the error control, which implies flow and sequence control with error recovery. We will come back in a minute to this. Then we have the so-called function which is called packet delineation. Remember that any layer 2 must somehow deal with this function. What does it mean, packet delineation? Well, the physical layer is dealing with bit or symbol transmission. Okay, so you take 1 bit or a small group of bits and you send, and on the other end you receive. That's what the physical layers in the 2 devices is doing. On the one end, you send bits or symbols. On the other end, you try to detect and receive with no errors, if possible, no bit errors, bits and or symbols. Now, this sequence of bits actually has no meaning from a physical layer point of view, but from our perspective is actually composed by values which are derived from packets. So we generate packets according to the application that the user is generating, and we need to send them. Packet is, of course, is a sequence of bits, but every packet has a specific meaning. It has some header with some meaning in the header fields, etc., etc. So we need to extract from this bit stream where the packet boundaries are. So suppose I'm sending 10 packets back to back. Every packet is 100 bits. On the physical layer, we will see 100 times 10 bits, 1000 bits, okay? One after the other one, with no distinction among them. But at the receiving end, I need to know that I have to chop them in 10 pieces, each of them composed by 100 bits. And the only protocol that is able to do protocol layer that is able to do that is the layer 2, which has a notion of what a packet is. The physical layer has no notion of what a packet is. It just knows what a bit is. Okay? So that's the called packet delineation function, which means dealing with packet delineation, which is defining packet boundaries somehow at the transmitter, and using the same packet boundary definition techniques at the receiver to distinguish where a packet starts and where a packet ends. That's the packet delineation function. Okay? We will see that we also have an addressing function. It's actually derived from historical reasons in a point-to-point link where you have one transmitter on one end and one receiver on the other end. Even if the link is bidirectional, you can treat it as 2 unidirectional links in the 2 directions. So I'm connecting A and B with a bidirectional link. I'm connecting A with B, with A as a transmitter and B as a receiver on one unidirectional channel. And I have another unidirectional channel from B to A. They are completely independent. Okay? So in this unidirectional channel from A to B, for example, there is only one transmitter and only one receiver. And whenever you send, I know that it's not A which is sending because there is no other transmitter active. And whenever I'm receiving, I know that it's not B which is receiving. So there is no real need for addressing in this scenario, okay? Still, we have an address for a reason that I will explain in a moment. And then we have the flow and sequence control with error recovery. So we want to be able to detect whether there is an error in each packet or not. We want to detect whether there is a proper sequence reception of packets. So we need to number packets so that if I'm getting packet 1, 2, 3, 5, I know that packet 4 has been lost. Of course, in a point-to-point link, packets are never lost. Packets are actually received with errors. And remember, whenever you get any data with an error, it's like not having received anything. So it's a loss. It's equivalent to a loss. Okay? There are two main reasons when you send data from a user to another user for packet losses. One is bit error transmissions on any link. If you have on any link some bit error transmission, the packet is dropped, so you don't receive it. And the other reason is by buffer overflow in packet switching networks. Because in packet switching, you get a packet, you store it, but if the buffer is filled up, you don't know where to write it, and then you have to drop it. These are the two main reasons for packet losses. Now, clear in this case, in a point-to-point link, there is no buffering, which is one transmitter, one channel, one receiver, so the only possible reason for losing a packet is bit errors. There is no queuing, right, in a point-to-point connection. Who knows, or if you want, who remembers what a flow control is? What does it mean, flow control? That's a very important concept from our class perspective. Yes?
It's the control of how much, if I remember well, how much space does the receiver has in the receiver window.
That's the way in which you implement flow control, okay? But the concept of flow control, yeah, correct. So he's saying that basically there is... Exactly. The goal of flow control, let me repeat it for everybody. If I don't repeat your questions, remember that I have to do that because I checked in some video lessons and you can hear my answer, but the question cannot be heard through the microphone, so I need to repeat it. So what he's saying is basically that flow control is a technique, and then he will give some detail. He gave some details about how you can implement that to avoid that a slow receiver can be overwhelmed by the bits or the packets received by the transmitter. So if you are sending packets too fast with respect to the ability of the receiver to get them, that's not a good idea, because you are putting packets on the link, and then those packets are dropped by the receiver, and then you have to retransmit again and later. So there is no point in sending if the receiver is not able to store them. Okay, that's flow control. The receiver wants to avoid to be overwhelmed by a too fast transmitter. Okay, clear? That's the concept of flow control. It's one of the very important concepts we have to remember in our class. It's one of the top problems in networking. Now you may say, what's the meaning of low or fast or slow receiver? What does it mean? I mean, you have a point-to-point link, the given bit rate. Suppose that the bit rate is 10 megabits per second, so it means that you are sending exactly at that bit rate, and you are also receiving at that bit rate, right? So if the receiver is able to receive at 10 megabit, what does it mean a slow receiver, right? It's not clear. And indeed, this is true. I mean, if you build a point-to-point link at a given speed, you put a transmitter able to generate bits at that speed, and you put a receiver able to receive bits continuously at that bit rate, of course. Otherwise, you cannot sell it, right? You are not selling to any customer if the point-to-point link normally is going to 100 megabits per second, and if you try to push 100 megabits, you are not able to get it out, okay? So by definition, a point-to-point link at any speed, the receiver is able to get the bit rate, okay? But it's not a problem of receiving the bits, it's a problem of managing the flow of data at the node level. So you have a bit generation, which is derived from a packet generation process, and the receiving end should get the bits, extract from the bit the packet, do some operation of the packet at many protocol layers, and you do that by a CPU at the receiving end. And typically this CPU may be shared, at least partly, with the CPU needed to get the bits. So you may have a slow receiver because that receiver is overwhelmed by other tasks which are not dealing with bit reception only. And in that case, it becomes slow. It becomes not able to deal with that bit rate speed because you don't have enough CPU to process the data. Okay? So that's why the receiver can become slow. Now, if a receiver becomes slow, what you can do, you can try to ask the transmitter to slow down. There is no point to let the transmitter keep sending the packets one after the other one, because sooner or later, if you keep doing that, you have to drop them. Okay? What's happening is that, you have here a transmitter, you have a unidirectional link, and you have a receiver here, right? And the receiver is getting the data in a buffer. Now you are filling up this buffer at the link speed, right, at the link rate. If the transmitter is sending data continuously, which is the worst case, okay, you may have a transmitter which becomes idle, better, it's easier, right? So that's the worst case, a continuously transmitting transmitter, okay? So you are filling up this buffer at the link rate, and you are amping up at the rate by which the receiver is able to process the data. And processing means everything I said before, receiving the bits, recovering the packet format, checking the packet header, checking for errors, maybe asking for a transmission, everything, all the function that you need to run, okay? So if the rate at which you empty out this buffer is lower than the link rate, normally it is not. Normally you are faster than the link rate. But it may happen that sometimes you become slower. That buffer will fill up, right? It's like a token. It's like a bucket, sorry. You fill up the bucket with water on the one hand, and on the other one, you are emptying it up, right? And if for some reason the process of emptying it up becomes slower than the process of pouring water in, the bucket starts filling up, okay? Until when? Until you fill it up completely, and at that point, you start pouring water out. And when the buffer is filled up, you start dropping packets. Exactly the same, okay? So you want to avoid that. And that's why typically what you do is that you manage and you check your buffer at the receiver, and when you detect that your buffer is starting to fill up too quickly, you will tell the transmitter in some way, slow down. That's flow control. So the flow control is coming from the receiver to the transmitter. You monitor here the buffer occupancy typically. That's not the only way of doing it. It's just one possible way of doing it. And when the buffer occupancy becomes too large, and we have to define in a more formal way what too large means, but intuitively, when this becomes too large, you tell the transmitter, slow down. This can be done in a more sophisticated way, in a on-off fashion, which is easier, okay? Shut up, start again, shut up, start again. It depends. There are many ways of implementing it, doesn't matter, okay? That's flow control. Clear? Clear? Some of you did like it, but I was not sure whether it was a real yes or just, to let me go ahead. Okay, so that's flow control. Sequence control, it's clear. Error recovery, I'm detecting an error, I drop the packet, and somehow I need to retransmit them to get it through, okay? These are the three functions besides packet delineation we used to have in layer 2. And then we have addressing, I will come in a moment why we need it. It's not so important from our perspective, actually. And what do we have in the packet layer? Well, we have the possibility of defining and creating virtual circuits. So before starting to send the data, we have to open a virtual circuit to make sure that the receiving end is willing to do that, okay? And everything that is managed in the virtual circuit, so opening it, closing it up, and whatever else you can imagine, okay? All of those functions which are dealing with virtual circuit management are there, clear? And furthermore, you still have, and you have again, flow and sequence control. And you may say, why is that? I mean, we have already flow and sequence control at level 2, and then we see that we have a flow and sequence control at layer 3, and that's a nonsense, right? I told you that we need to have a layered architecture. One of the main reasons is to organize things, to avoid repetition, to make sure that this layer is doing that and this other layer is doing something different, right? And now we are coming with the first architecture we are reviewing, and in the first architecture there is a repetition. Two functions which are flow and sequence control are repeated, right? At layer 2 and layer 3, and that sounds a little bit strange, right? Well, it is strange somehow. There are two reasons why is this way. First of all, not always when you define an architecture, you are going to use the full protocol set that you have defined in your network. Sometimes you use just a subset of those layers. So you may, for example, end up in some architecture using layer 3 of X25 to create virtual circuit on top of another layer 2, which may not have these functionalities. This typically happens, and this is due to many, many different reasons. You need to keep compatibility with previous networks that are running, and for several reasons. So first of all, when you define an architecture from scratch, typically you avoid this. But even if you do that, real architectures are very often a mixture of different architectures that have been designed maybe at different times with different goals, and so that may happen that you will see some repetitions or something like that. That's one motivation, that you will find repetition, I mean doing the same or similar function in more than one layer, okay, which is clearly not really a good idea. Furthermore, in this specific case, there is another reason, and the reason is the following one. Now take a little bit larger picture into account. So remember that our standards defines what's happening at this interface here. Okay, you have a user, and you have the first node to which the user is connected. Then you have a network, which you don't know the details and may be complex as much as you wish. And then you have again the user. And here you are defining that architecture we have discussed in 3 layers. Okay, so you have 3 layers here and 3 layers here. Now, at layer 2, what's happening is that on this physical link, well, it may not be a physical link, but for simplicity, consider it as being a physical link. Okay, you ensure flow control between the transmitter and the receiver. So regardless of whether user U1 is generating data for user U2 or user U3 or user whatever UI, doesn't matter. You may generate at the user level for many destinations, right? If you have many parallel connections, that's possible. All of those go on this physical link here, correct? So at layer 2, you take the summation of all of those connections, user-to-user connection, and you flow control them together, okay? To ensure that on this link, this receiver, when you are getting data from the user, is not overwhelmed, and on the reverse direction from the node to the user, again, to ensure that the user is not overwhelmed by everything running on that physical link. That's what the layer 2 is doing, okay? Is it clear? Any question? But this user, for example, may have been opening a couple of virtual circuits at layer 3. That's why we have this, right? So you may ask to open a virtual circuit here with user 3, and the blue one and the green one to connect to user 2. Okay? Those are 2 independent virtual circuits. Of course, they will use 2 different labels because you need to distinguish them here, right? So the red one will be label 3 and the other one will be label 5. And you will, of course, set up all of these intermediate nodes in order to ensure that for the green flows, you will follow this path, and for the blue and for the red one, you will follow the other one, okay? And whenever user 3 is getting data with the red label, he knows that this data has been generated by the user 1, okay? He may in parallel receive other data, for example, from user 2 on a different label. Clear? That's the picture. Now, suppose that for some reason you need to flow control the user-to-user communication. So the red communication from user 1 to user 3 becomes slow for some reason, okay? Now you want to avoid that the user 1 is generating on the red virtual circuit too much data, okay? So it's a flow control user-to-user, not over a link, over a virtual circuit in this case, right? So you want to slow down user 1, but you don't want to slow down user 1 with respect to any transmission, only for the red virtual circuit, because only user 3 is slow. How can you do that by using flow control at layer 2? It's not possible, because layer 2 is not going to distinguish between packet with the red or the green label, because you have no idea about the red or green label, okay? So the only thing that layer 2 can do is to slow down traffic on this point-to-point link. But if you want to slow down only the packets generated with the red label because user 3 becomes slow, you need to have a flow control at the virtual circuit level, independent for each virtual circuit. So user 3 will slow down packets generated by user 1 on the red virtual circuit. Okay, suppose that the flow control is stop and go. When you get a stop from user 3, you will slow down only, you will block actually only that flow, only the packet generation with the red label, while the green one can keep going. Okay, is it clear? Whereas if you have a problem on this link, because the first node physically becomes a bottleneck, at that point the flow control at layer 2 will come into place, and you will stop user 1 at layer 2, which means you will stop all of the virtual circuit, because any virtual circuit is generating on this link. You want to stop them all. That's why layer 2 now needs to come into place. Is it clear? So actually, even if it's a repetition of functionalities, is flow and sequence control again, it has a meaning in this architecture, because in the one case you block the link, in the other case you selectively block a single virtual circuit. And you may have several virtual circuits sharing the same physical link. Clear? I'm particularly asking that for those of you that have a little knowledge about networking, because these concepts are fairly basic for those of you that have followed already class, but they are fundamental building blocks to keep going. So if this is not clear, just try to revise and study a little bit so that in the next week it's very clear and very easy to come with these concepts, which are not difficult, but if you see them for the first time, you have to put them in a proper way in your mind. Okay? Have any question about that? No. Okay. So flow and sequence control at layer 2, flow and sequence control per virtual circuit, independently on each virtual circuit at layer 3. Okay? So these are the main features in terms of what this architecture is doing, which service is providing. Okay, if I'm using that, I can get these features. So I have a link by link error control, I have a flow control and sequence control on the link, and I have a flow control per virtual circuit. Okay? This is what, if you want to describe it qualitatively. What else? Well, and this is, well, we already said that. This is what does it mean dealing with bit errors. We are talking about error recovery with retransmission in this case. So layer 2 error recovery with retransmissions. Okay, that's what the standard states. Some details, some repetitions. This, I should just cancel this slide. I don't know why it's there. I should have dropped it, sorry. This is absolutely detailed. Cancel, slide 100 is completely useless. Okay. This is a summary of flow and frequency control. Now, what is written here, there are some details. Now, how do we typically implement flow and sequence control? And remember, sequence control implies ability to detect errors and asking for retransmissions through what is called window protocol. Who has no idea about what a window protocol means or a retransmission protocol means? Everybody knows that? You have no idea? You are the only one? Really? So who is coming here to explain what a window protocol is? Not you. Somebody else. No, you don't have to come here. Tell me what a window protocol is. Why it's called window protocol, which are the features, which is the basic idea. Come on, none of you raised your hand, so now you have to explain, right? Otherwise, you are cheating. You are a friend of him, doesn't it? It's not fair. You are also a friend of him. You are sitting close to him. Go ahead, I'm kidding. Window protocol? What is an ACK?
It's an average packet.
That's not the best way of starting to explain to somebody that does not know what it is, right? So, okay, this is just, no, thanks. Yeah, you are right. Remember that when you come to the exam, okay? If you get a question, like for example, scheduling algorithm, that most of you today don't know exactly what does it mean, explaining what the scheduling algorithm is, that's not the proper way of starting, okay? You start saying, okay, the scheduling algorithm is here to do this, and this specific one is working in this way, and you have to explain things like I knew nothing about it, okay? So he started saying, okay, you are sending acknowledgement without explaining why we have acknowledgement and so on and so forth. So what's a window protocol? You have to start with the basic idea of retransmission scheme. So the idea is that I'm sending you a sequence of packets, and as a consequence, in order to get message from you whether you have got it or not, I need to number them, first point. So first of all, we assume that I'm sending a sequence of packets. If I'm sending only one, there is no concept of sequence control. And I'm numbering them. So the first thing is that I'm numbering packets one after the other. I send you packet 0, packet 1, packet 2, packet 3, packet 4. Packet header contain number, which are increasing from 0 up to the number space we have available. Okay? So that's the first thing. Then as a receiver, what's happening? You get a packet and you check the number, right? And if you are getting packet 0, 1, 2, 3, 4, 5, 6, 7, 8, etc., perfect. No errors, everything's fine. And then at a given point, you don't get packet 7 for some reason. What does it mean you don't get packet 7? Actually, in a point-to-point link, you get the packet physically because you get the bits, but you have an error, so you drop it. When you detect an error, you discard everything, and so you will not discover packet 7. Now, there are two options. One is to say, okay, the receiver at that point is saying to the transmitter, send this packet again. That's one possibility. The receiver tells the transmitter, I didn't get packet 7. Okay? That will work very well in this scenario in which you have a link, a physical link at the point-to-point one, because if we got packet 1, 2, 3, 4, 6, as soon as we get packet 6, we know that packet 5 has been lost, for sure, because we are getting packet one after the other one in a point-to-point physical link. In general, this may not be true. If you are in a connection which is a logical connection, you may end up sending packets in order. This packet may follow slightly different paths, and maybe you can get packet 6 before packet 5. That may happen in general. And in that case, relying on the receiver for asking for the retransmission is not a good idea. So the basic idea is, number one, numbering packets. Number two, you send packet, and the receiver is telling you, I got it. I got packet 0, I got packet 1, I got packet 2, I got packet 3. And you wait, okay? You wait a given time, and you expect to get this answer which says you, okay. So I'm sending packet 0, I'm starting a timer. I'm sending packet 1, I'm starting a timer. I'm sending packet 2, I start a timer. And I'm waiting an okay before the timer expires. Okay? If you get it, fine. If you don't get it, by the time, the ACK. That's the ACK. I'm telling you I got this packet. You will send again. And then again, you will wait for the ACK, and so on and so forth. Okay? Is it clear, the basic idea? So, to be a little bit more precise, the easiest way of implementing it, yellow, no. I want to, no. You have a transmitter here, you have a receiver here, and you may say, okay, I'm sending packet 0, and then you send me ACK 0, and then I'm sending you packet 1, and I'm getting ACK 1, and so on and so forth, okay? That's the basic way of doing that. Now you send packet 2, and for some reason you don't get the ACK. Okay, why not? Well, because maybe packet 2 was received with errors. So the receiver has not got it, and it's not sending you an ACK. Or maybe the ACK has an error, so you don't recognize it as an ACK. For any of those two reasons. You don't get it in time. Well, after a given time, you send it again. Resend, retransmission. That's why these protocols are also called automatic retransmission protocol. After a while, I'm sending it again. If you don't tell me okay, I send again. And again and again until you say okay. That's the basic scheme. Okay? Is it clear? Any question about that? In this picture, we are plotting on the horizontal axis the distance, physical distance between the transmitter and the receiver. So if the two are farther away, the time, this is time, passing by to receive the data generated here is larger, because You have how it is called, this delay? Shut up, you in the first row. How is this called? This delay is called, which type of delay you are plotting here? Propagation delay. Okay, good. So the longer the link, the larger the propagation delay, the more time you have to wait until you get. Okay? Clear to everybody? Also to you that have never heard about window protocol? Okay. Where is the window here? Yeah, there is no window, or if you wish, the window is on, in the sense that if you do that in this way, suppose that the propagation delay is large, it requires a huge amount of time to send every packet, right? So suppose the propagation delay is 1 second, okay? And the packet size is 1000 bit. Now we are sending how much? 1000 bit every second, which translating which bit rate? Very low bit rate, right? And how can you increase it? Well, not easily, right? Yeah, you can increase the packet size because you keep sending 1 packet per second. So if the packet size is larger, you're sending more bit per second. But I mean, still, this is not scaling well if the propagation delay is large, okay? So in order to overcome that, what do? Well, you say, instead of sending 1 packet and wait for the ACK, you can send K packets, up to K. And the K is called window of packets. So you can send up to K packets, one after the other one, and then you have to wait. What? You will wait for Kx. When you get the Kx, you send again and again and again. So you have a cycles in which instead of sending 1 packet, you will send K packets, okay? One after the other one. So the bit rate increases. If the propagation delay is 1 second as before, but you can send K equal to 100 packets, you increase the bit rate by a factor of 100. Okay? That's the basic idea. So that's called window protocol. Clear to everybody? Everybody remembers that now? Or if you have never heard now, it's fairly clear? So that's how it works. You can send packets numbering them one after the other. You are waiting for ACKs. And depending on whether you receive an ACK or not, you keep going or not, or you retransmit if you don't get the ACK in time. Clear up to now? Now, let me see how important is this one. Let me check one thing. Okay. Okay, so this type of protocol is fairly simple to intuitively understand. There are a lot of details behind them, okay? There is a lot of complexity when you really want to implement them. You have a lot of options in implementing them. We don't have the time to go through many of those options. I will give you just few hints here, and then we will revise this much later in the class when we will discuss about congestion control approaches, and one of them is based on congestion control run through the TCP protocol in the internet, and then we will revise that a little bit more in depth, okay? You see here something that you can almost understand fully, which is stating that the transmitter window is negotiated, is the number of packets you can send, that's the window. How many packets I can send without getting the ACK, okay? In this case, you see that the number is very small, just 2 packets. Why? Because this is a standard which is dealing with link by link. So in the link, the propagation delay, even if the link can be not very short, is typically very little. So if the propagation delay is little, with a small number of packets, you can still get high throughput. Let me add something about this here. So suppose that this is the propagation delay. This time here is called, as many of you remember, it's called round trip time. RTT, it's called round trip time, okay? And as I said, the larger the round trip time for a fixed number of packets that you can send without getting the ACK, the larger it is, the smaller is going to be your bit rate, okay? So if you can send, suppose, only 1 packet, by the way, this time here, it is what? If you want to answer during the class, you have to move to the next row, not in the first row. First row is not allowed to speak. What time is this one? So this time represents what? Okay, this is the first bit in the packet, correct? And this is the last bit in the packet. So this distance here, horizontally, is the packet size in which dimension? Remember we have seen last time 3 packet size dimension. One packet size was in bit, right? The amount of bits in the packet. The second one was in time. Which time was it? The transmission time. The time needed to push the bit on the link, which depends on the packet size and on the link bit rate, correct? And the third dimension was in meter. How much space do you occupy, which depends on the packet size, and how much time you leave to the first bit to propagate while you are sending the other bits. Okay, do you remember that? So in this picture, this green part here is the transmission time of that packet on this link, which depends on the packet size and on the link speed. Clear? If you double the link speed, the packet size will be reduced by half in meter because the transmission time is half. Okay? If you double the link speed. Clear? So in this picture, if you double the link speed, the packet size in meter becomes half, and as a consequence, actually, and this is the consequence of the fact that the packet transmission time is reduced by half. Clear? Any question? Also in the back there, you are more shy typically because you sit in the back. Okay, so we have seen here. This is propagation delay. Right? The green one is transmission delay. Correct? And if we double the link speed, the transmission delay becomes half. Clear? Okay? Now the question is, for those of you in the third row, you are in the third row, yes. If I double the link speed, so I'm moving from the green picture to the yellow one, okay? Is it changing something in terms of how many bits I'm sending per unit of time from this transmitter to this receiver? Which is the answer? Again, the question. Suppose that we are comparing the green case with the yellow one. In the yellow case, we double the link speed. So what's happening is that you reduce by half the transmission time and also the space occupancy of the packet. And the question is, in terms of how many bits this transmitter is pushing on this link, under the hypothesis that you send one packet until you get the ACK and then you send another and another. Is this changing in any way the bit rate of the transmitter, yes or no, or it depends? What's the proper answer? Third law. Who is voting for is not changing anything? You are not in the third wall. Come on. Who is voting for it depends? He's voting for it depends because I said in the first lesson, 90% of the time, the correct answer is it depends. So if I'm raising my hand, I will get 90% of chance to get the proper answer. In this case, you are wrong. It's not changing anything. Why is not changing anything? Because you are still sending one packet per round trip time. The only thing that is changing, it takes a little bit less time to send it out, but then you have to wait until you get the ACK to send another one. So at the end, you are sending the same amount of bit per round trip time. Correct? Not exactly, for those of you that are a little bit more sophisticated, but as a first approximation, what I'm saying is correct. Okay? So it's not changing anything. Why? Because what is running here, what is controlling the bit rate is the amount of packets I can send per round trip time. And if you tell me that I can send only one, regardless of the speed at which I'm sending this single packet, I'm still sending 1 packet per round trip time because the window is 1. So I'm limited by the window protocol. The window is too little. Is it clear? If instead you say to me that, well, suppose that this picture more or less scales, you can send up to 3 packets per round trip time. The window becomes 3. Which bit rate I will get? If this picture scales in the proper way, which bit rate I will get with respect to the link speed? I can send up to 3 packets, and then I have to wait, right? For how much time I am going to wait? Half of the round trip time. For how much time I'm sending? In this case here, with k equal to 3, I'm going to be sent bits for this amount of time, right? And then I have to wait. What? To get the ACK. How much time I wait? This time here. And these 2 times are, again, as a first approximation, these 2 times, this one and the one from here to here, are similar, equal, double of, are equal. Half of the time I'm active, and I'm covering the left to right channel with buckets, and then I have to stop, because k is equal to 3, until you get the ACK coming back. And the ACK are coming back exactly at the same speed of the packets. So I'm active 50% of the time. 50% of the time I'm sending my window, 50% of the time I'm waiting to packets to come back. So that's not enough to get the link speed. I'm getting half of the link speed. If I want to be able to send continuously, I will need k equal to 6 in this case. Okay? With k equal to 6, I can keep sending continuously. Because in this case, k is equal to 3, I can send 1 packet more, and in the meantime, 1 ACK is coming back. So if k is equal to 6, let's use the blue part here, I will send 3 packets here, then I will have 3 ACKs coming back. The ACK is smaller just because it does not contain data. In the ACK, you have only the header. Okay, so it has less bits, so it requires less time to be sent. But the spacing between the ACKs depends on the packet size, because you can send the ACK only when you get the packet, and you get the ACK after 1 packet transmission. Okay, so at that point, with k equal to 6, I should stop, right? K is equal to 6, but I got 1 ACK, so I can send 1 packet more, right? Then I should stop. But again, when I finish sending that, I get another ACK, and so on and so forth. So in that case, with k equal to 6, I can send continuously. I will get the bit rate of the link. Okay? So that's how this is the interplay between the round trip time and the number of packets in the window. You should have enough packets in the window to allow you to keep sending. And then when you start getting the ACKs, okay, that's enough. You don't need any k larger than that. K equal to 6 is good enough. K equal to 3, half of the bit rate. K equal to 1, 1/6 of the bit rate in this case. K equal to 12, still the link speed. Of course, you cannot increase behind that. So if you keep it larger, you simply are buffering packets here, because you can send other 6, but you don't have the speed at the transmitter, physical speed to push them on the channel, right? So they are stored at the transmitter buffer, waiting to be sent out. So you still get full bit rate. You don't gain anything more, of course, because that would be physically not possible. Okay? So if the round trip time is small, the shorter link it is, the smaller the window can be. That's why we have seen W equal to 2. It's negotiable, that's the default value, but still is a small number. Why? Because the round trip time is little, so few packets are enough to allow you to send at the maximum speed. Okay? Is it clear? Let me write one important rule about window protocol. The bit rate that you can get out of the window protocol is equal to the window size which is, sorry, divided by the round trip time, which is equal to K, K times packet size divided by the round trip time. That's the maximum you can get if there are no errors. If there are errors, of course, you have retransmission, so the performance becomes worse. That's the bitrate you can get with the window protocol. As long as K is not large enough to reach the link speed, you are limited by the window protocol. The window is not large enough. As long as K becomes large enough so that this ratio is larger than the bitrate of the link, of course you are going to the link speed. Okay? In other words, if you have a K which is too large with respect to your need, in our example it was, for example, K equal to 12. K equal to 12 is double what you need, right? What you are actually doing is that you increase the round trip time because you buffer at the transmitter. So you double K, you double the round trip time because you have half of the packets waiting there, and that's queuing delay, which becomes round trip time because it becomes delay that you have. You make it 4 times larger, you have 3/4 of the packet in the buffer, and you increase the round trip time. So this ratio will never exceed the link speed. If you take K larger than the minimum now, you are actually, in some sense, increasing also the round trip time because you have buffer at the transmitter. Okay? That's the rule that tells you which is the maximum speed that you can get from a window protocol. If you need K equal to 6 and you have K equal to 3, you are going to get half of the maximum possible rate, which is the link speed. Clear? Any question about that? So that was a very quick review for those of you that know that. For those of you that had no idea, maybe it was too quick, but you can go back and make it a little bit more clear while you revise things. Okay? So that's the window protocol at layer 3. Okay, and so that's the value that you have. And you see here it's written that you have cumulative acts. Now, cumulative ACK is exactly one of those options I was mentioning. Okay? What does it mean, cumulative ACK? It means that normally what you would expect is that I'm sending you packet 0, 1, 2, 3, 4, 5, 6, and you will send me back ACK 0, 1, 2, 3, 4, 5, 6. Okay? That's one way of doing that. That's called selective ACK. It has some advantage, but it has also some disadvantages, in the sense that if you don't get ACK5, because the ACK5 is lost, you have to resend packet 5, right? So I send you 0, 1, 2, 3, 4, 5, 6. You get all of them, but ACK5 is lost. And so as a transmitter, I don't get the ACK, I have to resend it. Okay? Cumulative ACK instead, you send an ACK telling the transmitter, I got everything up to 6. So you send again ACK 0, 1, 2, 3, 4, 5, 6 as before, but ACK 6 means I've got everything up to packet 6 included. So if you lose ACK 5, whenever you get ACK 6, you are okay. You are compensating for ACK loss through the cumulative ACK. Okay? So that's what's the meaning of cumulative ACK. Whenever you send an ACK, you tell the transmitter, I've got everything up to this packet. Okay? Of course, if you get packet 0, 1, 3, 4, so you lose packet 2, 0, 1, 3, 4, when you get packet 3, you have to say ACK 1, because the last packet that you have got continuously with no hole is packet 1. So you are losing some information. Okay, so there are also drawbacks with respect to the cumulative ACK. But the meaning of cumulative ACK is that you send an ACK telling that at any packet, telling the transmitter, I've got everything correctly in order up to this packet number. Okay? So if you get packet 6, you say ACK 6, which also means ACK 5, ACK 4, ACK 3, ACK 3, ACK 1, all of the previous one also. Okay? And that compensates for ACK losses. That's good for ACK losses. Cumulative ACK is good for ACK losses. Okay? Clear? The other one are details. This is just a little bit of a format. I don't care so much. Very quickly. Here, in a very strange format, but we don't care, that's a layer 2. Whenever you have a virtual circuit, don't look at the slide, look at me. I know that I'm not so interesting, but still look at me. Whenever you have a virtual circuit technology, and I'm asking you what you would expect to see in a packet header, given that this is a virtual circuit technology, the answer will be good. 2 weeks, very well. The label, right. Remember, in a virtual circuit technology, we are identifying the address through the label. So since in packet switching, every packet is carrying address, so the first answer will be the address. In any header, there is the address, for sure. In the particular case of virtual circuit, the address is actually the label of the virtual circuit. Okay? And indeed, these LCG or LCN numbers, acronyms, are actually the labels, in this case, of layer 3. Okay? There are 2 labels. If you remember, I said that there are 2 labels because this gives you the possibility of grouping virtual circuits, and that's exactly how they are called here. So we have basically the labels. Okay? Plus further details which are not interested in. Whereas here, at layer 2, which is the LAP-B protocol, if you remember, what do we have? Well, the info, which is everything generated by the user. Actually, everything generated by the higher layer protocols, we will see a little bit. Then what we expect to have here, look at me, not the slide. So we know what the layer 2 is doing, right? What is the layer 2 doing? Functionalities of layer 2. Receiving bit is a function of layer 1. Rebuilding the packet from the bit stream, okay? Right, which we call packet delineation, okay? So packet delineation is one function, then what else? Addressing, and we should understand why we need addressing. Then flow sequence and error control. So what do we need to do error control? We need some error bits, right? That in this case are called CRC. So we expect to see some error bits, something that allows us to delimit the packet, and something that allows us to number the packets, and some addressing scheme, because any protocol is addressed. And indeed, we see that. So the packet delineation is obtained through two delimiters, which is a conventional sequence of bits that you will only find at the beginning or at the end of the packet. Okay, so whenever you detect it, that's the beginning of the packet, that's the end of the packet, that's the beginning of the next packet, and so on and so forth. That's the basic idea. That's the delimiter. The CRC is one of the techniques to do error detection. Okay, there are many of them. This is one of those. You see that the number of bits is fairly large to do that. The address, strangely, we have only one address. Normally, we have a source and a destination address, typically. Okay. In this case, we have only one address. I will explain you why in a moment. And normally there are 2. Normally, unless you have a circuit switching, a virtual circuit packet switching technique, in which case you have the label, not the address. But layer 2 is not virtual circuit, so we have the address. And then in the control field, depending on which type of packet we are analyzing, there will be some space for packet numbering and also ACK numbering. Because I'm sending the packet 0, but when you send the ACK, you have to write ACK 0, so I need also the ACK number. Okay? And this is more or less what we would expect, knowing the functionalities. It's very unlikely that I will ask you at the exam anything about packet formats. Okay? Unlikely does not mean it's impossible, but it's unlikely. But in any case, even if I'm doing that, because that day I'm very bad, don't panic. Okay, because if you remember what this protocol is doing, then you can derive most of the information about the formats, okay, as we have done right now. We know the functionalities, we know that there should be some way of doing the delimitation, the delineation, we need some addressing, we need packet numbering, ACK numbering, we need some error detection, and the packet format is coming out. Of course, you may not remember the size of the packet, the order, but it's not so important. So in the next set of slides, there are some more details about that. So these numbers here are the size of the fields. We don't care. This sequence of bits is the values that you will get as the delimitation in this packet format. And standards are there also to define all of these boring details. But without boring details, networks would not work. So we will not be able to spend and badly use our time writing, for example, on social or something like that. It would not be possible at all. So that's why we are going to take some attention to standardization efforts in this class as well. The control field for some packet PDU will carry the information related to the packet and ACK numbering. The CRC is 16 bits, 2 bytes. And what about the address? Well, very quickly, this protocol has been designed in this scenario, which has nothing to do with networks. It's just a very old architecture for workstations. Actually, they were called mainframes at that time. I was very young at that time. Probably I was not even born at that time. So in this type of architecture, we had a master there, which contains everything. Okay, CPU, disk, and memory, and everything. All the intelligence is there. And then we have this dumb, stupid slaves. I know that this terminology is not really politically correct today, but this is how they were called. And these were terminals with just a keyboard and a display, which was not a graphic display, just character-based display. Okay. So what you were doing is that you were writing something and sending commands to the master, and the master was answering to you. That was how it was working. And in this context, we had actually two types of scenarios here, because this is a bidirectional channel, but on the downstream phase. So if you consider the channel from the master to the slaves, okay? How many transmitters do we have if you consider the unidirectional channel from the master to the slave? How many transmitters are active on this channel? One, just the master, right? How many receivers? The number of slaves. So we have one transmitter, many receiver, and that's a problem of channel sharing, which we have defined as, you are in the first row, shut up, which has been defined as channel sharing. We have only two possibilities, so it's not so 50% of chance multiplexing, right? One transmitter is a centralized problem. All of the data are in the master, and you have to send to the slave, okay? On the other direction, we have several active transceivers, which are the slaves, correct? And one receiver. That's instead a multiple access problem. And we need to ensure that slaves send at different time if we want to solve it in time, or a different frequency, or a different code, or a different whatever, okay? Clear up to now? Now, what's the relationship between this and the address? A lot. So when the master is sending the data, which address do you need? Only the destination, right? Because you need to address the slave. Because if on that channel only the master can send the data, well, we only need the destination address, which is the slave address, okay? On the other hand, when the slaves are sending to the master, which address do you need? Again, the slave address, which is the source in this case. So that's why there is only one address field, okay? It's always sometimes the destination, sometimes the source, depending on whether you are a master or a slave. Now, in normal protocols, like in our case, what's happening is that the two-end system are exchanging this role of master-slave depending on the type of PDU that they are sending. And depending on that, that address field will contain either my address, if I am a slave, or your address, if I am a master, during that period of communication. That's why there is only one address, okay? Do we care? Not much, but just for completeness. I mean, do we care for this class? Not much. And in the control field, so we have said a lot about this. We said something about the limiter. In the control field, what do we have? Well, we have different type of PDUs. What does it mean, different type of PDUs? Well, we are not only sending data, okay? Some packets may carry data, some other packets may carry control information, and we need to distinguish among them, okay? So just to give you an example, when you send an acknowledgement, that's a packet which carries no data, right? And you have to distinguish from packets carrying the data. Okay, so that's what the control field is doing. It tells you, okay, this is a packet, this is an ACK, or this is a control packet. It has nothing to do with the data flow of the user, right? I want to send you a command or whatever to manage something. And this is what the control field allows us to do. If the packet is what we call by a packet, a user packet, then the first bit is 0, and you have 3 bits only to number packets and ACKs. If the first 2 bits are 1, 0, this is an acknowledgement. The supervision field, the supervision type of PDU is the acknowledgement. If it's an unnumbered one, it's a control packet. Okay? That's it. Information is the data sent. Supervision are the ACK. The unnumbered one are management function like link management or some other options. Okay? Some details. There are several types of ACKs. So I just put the slides for completeness. It's not so important from our perspective to know these details. Okay? If you are interested, you can find some information on the slides, some information on the books. But from our perspective, it's not so important. Okay? So lesson learned, what's important for us. First of all, I would like that everybody has at least a basic notion about what a window protocol is and which are the features of a window protocol. Okay? The basic functionalities. It's the basic way of doing error control and flow control. First lesson learned. Second lesson learned, in this case of architecture, we have 3 layers, which are doing different things, but we are also detected some repetition. For example, flow and sequence control is repeated at both layers. Okay? These are the 2 main observations. I forgot something, and the something that I forgot is about flow control. I told you at the beginning that, where is it? Here, there is flow control, both on data link layer and layer 3. On the one hand, on everything, on the other hand, per virtual circuit. How do we implement flow control? Well, there are several options, but now that you know that there is a window protocol and you know that how the window protocol is working, a nice way, which is the most popular one, of implement flow control is to act on the window size. Because the window size, if you remember, this is the rule. That's the most important lessons learned from the knowledge of window protocol, this rule. The bit rate is the window divided by the round trip time. So how can I control the bit rate? Well, you may say I can increase the round trip time, right? If you want to reduce the bit rate. I could increase the round trip time, for example, by delaying the ACK. I don't send you the ACK. You don't get it, you slow down. But this has a drawback because after a while you will retransmit. Correct? The other way is to reduce the window size. So by acting on the window size, I can do flow control. I can reduce the rate of the transmitter. Clear? And that's what flow control is doing. In this case, in this example, in this protocol, this is done in a very rough way, which is sending a packet which puts this window equal to 0. Okay? Which stops completely the transmitter. Because if your window is 0, you cannot send anything. So it's a stop and go flow control. When I'm in trouble, stop. And if I'm doing that, after a while, I have to give you again the go message. Otherwise, you will stop forever. That's how the flow control is implemented here, with a very simple stop and go procedure. Window either 0 or maximum, binary information. Okay? That's one example of implementing flow control, and you see it here. You have one control packet, which is an ACK, an acknowledgement, so ACK3, with the information that the receiver is not ready. So you block the transmitter. So I'm telling you, I got packet 5, shut up. That's the receiver not ready. If I'm telling you ACK5, I'm using the receiver ready with number 5. If I want to stop you for flow control, ACK5, stop, shut up, receiver not ready. And from now on, if the receiver is not sending anything later, which is another receiver ready, you will not start sending that. So it's a binary or on-off flow control. You see it here. On-off flow control. That's how flow control is implemented in this specific example, through the window protocol. So window protocols are used to do sequence, error, and flow control jointly. Packet numbering, error detection, ACK transmission, and window size control. In this example, shut off, go to the maximum, just a binary way of doing that. There are more sophisticated ways of implementing it, but the concept is the same. Okay? Any question about that? Okay. If not, 5-minute break, 6-minute breaks.